In the last video, we looked at average rate of change and how we can calculate that for any function. So now we're going to look at instantaneous rate of change and how that's different and some of the complications that arise when we want to try and calculate it. So recalling from previously that the average rate of change is the gradient of the secant between any 2 points, so a line that goes through 2 points on a curve or a function. Okay, so on my example down here, I would have a line going from here, this point, is that not working? From this point up to this point here, and the gradient of that line would be the average rate of change between those 2 points. So we could call them A and B. So that gives me that's average rate of change. But sometimes we want to be more specific than that, we want to be more accurate. Okay, we don't want to know what is the average rate of change, we want to know specifically what is the rate of change at that point A. And in order to do that, what we're looking for is the instantaneous rate of change. So that's saying, what is the gradient of the function right at that point, right at that instant, when it has a value of A. And of course, to find that, what we're now talking about is a tangent to that curve, okay, because the tangent represents the gradient at any instantaneous point on a curve. So if you could draw a tangent to that curve at that point A, then this is your instantaneous rate of change. So that's the difference between average and instantaneous. And you can see just visually there's quite a big difference there. This rate of change is quite steep compared with this rate of change. So there's obviously going to be some inaccuracies if we're just using average rate of change. So the average rate of change will get closer to the instantaneous rate of change as the interval gets smaller. Now, what does that mean? It's maybe a little bit sort of hard to get your head around. So what I'll do is show you a quick demonstration of this. Okay, so here we've got a curve, it's got a nice parabola. Alright, and we've got 2 points on the curve, and I'm going to move this point A, I'm going to make that 1, drag that over to there. Okay, so we're looking at between A and B. Ooh, there we go, so we've got a line through AB. Between A and B, we've got our average rate of change. So that blue line is the average rate of change. Okay, and I can see if I drew a tangent to A, it would be more sort of over here, so quite a lot less steep than that. But I can approximate this by reducing the distance. So at the moment here the distance is 2, because this is x equals 1 and this is x equals 3, so that distance is 2. But obviously if I reduce that distance and I bring this point B closer and closer and closer, then this line is going to get closer to the tangent. So we just reduce it, see it's getting closer and closer till we get to this point until they become the same. Oh, now what happens to the line? And then it goes the other way. So at this point it's the same, but why does the line disappear? And you'll notice down here we've got the equation of the secant line. So this is giving me the equation of this blue line, which is all fine while we're out here. It's not a problem until we get to here, which is where we want the equation. We want to know the gradient, and it won't tell us. And what's going on there? So we'll come back and have a look at that. But I'm just wanting to demonstrate that as you reduce that interval, the average rate of change gets closer and closer to being the instantaneous rate of change. Okay, so for an example for this, we want to estimate the instantaneous rate of change of y with respect to x at the point 2,9 on this curve. Okay, so it's talking about estimating, and it's saying, well, let's consider a secant where q is 2.01, so p is 2, so q is 2.01, so it's only 0.01 of a unit further along, so it's quite a small interval. Okay, so the way you do that, of course, using your average rate of change, we want to find what is the value of the function when it's when x is 2.01. So the easiest way to do this is actually on your calculator. Just get rid of that. If you define, so we had x cubed plus 1. So if we define that as x cubed plus 1, remember from our function work with functions, you can define a variable or define a function there. And now we can work out, well, let's say what's f at 2.01, and it tells me it's 9.120601, so we can use that on here. So 9.120601. 1. Okay, and of course the value when that's 2 is going to be 1, because 2 cubed is 8, sorry, is 9. So take 9, and then 2.01, take 2. So that's our change in y divided by the change in x. And when you work that out, you get 12.0601. Okay, so that's an approximation of the instantaneous rate of change. But that's what it actually is the average rate of change between 2 and 2.01, which is a small interval, but it's not entirely accurate. So what would happen if we let the x value, instead of being 2.01, we said 2.001. So now our average rate of change, and again you can go back to your function because we've done this, and we can just pop a 0 in there. And now it's a slightly smaller number. Okay, so we've got 9.012 and whatever it was, 06 something or other. Okay, minus 9. Now we're dividing by 2.001, take 2. And if you work that out, you end up with 12.006. So you can see it's kind of approaching 12 as we're doing this. And of course, the smaller that interval becomes, the closer we imagine it will get to 12, but it's never actually quite going to get there. So we know we can calculate the average rate of change using this formula, which is what we've been doing. And we know that the approximation to the instantaneous rate of change gets more accurate as these values get smaller, so as the change in x value. So basically it's the change in x value, not really the change in y, but the change in x value, so this is that interval. So as that interval gets smaller. Okay, and we often use, or we do use the Greek symbol delta, and delta can either be, that's capital delta, or lowercase delta. Okay, we use that to denote very small change. So if we were saying, well, delta x, that would be small change in x. Okay, and I just want to put that in because we'll sort of come back to that a little bit later. So small change in x, small interval. So the big question is, why can't we let a equal b to get the gradient to the point? Because that's what we want. If we let a equal b, then the interval is 0, and then we can get the gradient at the point, right? But if you pop that into there, if we say a equals b, what do you end up with on the bottom? You end up with a 0, and we all know what happens when we divide by 0. The universe implodes. So we can't do that. So we can't just let a equal b. So at this point we're sort of stuck. We can get a fairly close approximation, especially if we're using very, very small intervals, but we can't get right to that very point where we can calculate the instantaneous rate of change. So the purpose of calculus is to provide a solution to this big question. And of course this was something that good old Isaac Newton thought about. Clearly he decided that he wanted an answer to this and invented calculus in order to solve this problem, for which we are extremely grateful. So let's have a look at another example, just to sort of cement this in your minds. We've got a graph here, and it's measuring or it's representing the area covered by a spreading plant, okay, and over a time in weeks. So we've got weeks and the area in centimetres squared. The first bit says, well, let's find the gradient of the secant p to q. Okay, so the gradient there is just the change in y, which is your 600 minus 300. 300 over the change in x, which is 7 minus 2, which is 5, so that's 60. So the change is 60 centimetres squared per week. Okay, that's over that interval from p to q. But you can see that it's a shallower gradient here than it is up here, so that's not entirely accurate. So we want to pick a value that's a bit closer to p that'll give us a more accurate representation. Okay, because we want to find what is the instantaneous rate of change of the area of the plant at t equals 2, so at this point p. Alright, so if we work on q prime instead, now we've got 330 minus 300, which just leaves us with 30. And we've got 3 minus 2, which of course is just 1. So we've got 30 centimetres squared per week, which is half of what we said it was over here. So by reducing that interval, we get a significantly different rate of change for that point t equals 2. Okay, so this is all very well and good, but we can't yet do it without just an approximation. So let's have a look at how we can do this with our class pad. So we've got an example here where we've got a volume given by this function. We want to find the average rate of change between t equals 1 and t equals 3. Then we want to do an estimate. So we're going to choose this very small interval. And then I'm going to show you how to do it, so calculate it exactly with the class pad. So calculate exactly with class pad. Alright, so let's start with part A, and we're going to do what we did before where we define that function. So let's just clear all this. Okay, so we've got 3x squared plus 4x plus 2, and we're going to define that. That's fx, that's all good. Okay, now we had the interval 1 to 3, so our gradient is going to be the value at 3 minus the value at 1 over 3 minus 1. So let's go and find this out. So the value at 3 is 41. The value at 1 is 9. Okay, so we've got 41 minus 9. And if you work that out, you end up with 16. Okay, so that's an average rate of change between T1 and T3, T equals 1 and T equals 3. Let's do it now. We're going to say we want to estimate. So this means we need a small interval. So let's let delta x equal 0.01. So we're going from t equals 1 to t equals 1.01. Alright, so the gradient will be, well, we know it'll still be minus 9, and we know it'll be 1.01 minus 1, so we just need to find out what is the value of the function at 1.01, so we can do that up here. Okay, 9.1003. Alright, and if you work that out, you end up with 10.03. Okay, now this is a pretty small interval, so you could say, well, we're probably approaching 10, but we're not really sure. It seems reasonable, but we're not absolutely sure. But the class pad will do this for us. So if we go back into here, and we're going to say, let's just drag fx down. Okay, highlight. If you go up to interactive calculation, line, and what we're doing is finding a tangent line. Okay, because that is the definition of our gradient, our instantaneous rate of change, and we want that at the point 1 because we're interested in what is the rate of change when x equals 1. And it tells me that the gradient of that line, the equation of that line is 10x plus 1. And of course, if the equation of that line is 10x plus 1, then the gradient is 10, which is what we thought. Okay, so we can really sort of bring this home by graphing these two. So let's graph the function like so, and I'm going to just change this a little bit. Just go up to 3. Change it again. Not quite that big. That's a bit better. Okay, and then if I graph that line, there we go. So there's our function, and there's the line that is the tangent to that function at that point where x equals 1. So we can say for C, class pad says gradient equals 10. So just to summarise, we've got the instantaneous rate of change is the gradient of a function at a specific point. So for some value of x, some defined value of x, we can approximate this gradient by calculating the average rate of change over a very small interval, and that's where our delta x comes in. A small x. Also, you can use your class pad, which will do it for you, and it will give you an exact value. Now, we want to be able to do that without having to rely on our class pad, because sometimes we know we're not allowed to use it. And the way we do that is using calculus techniques. Okay, I'm not going to show you in this video, so stay tuned and we'll work out how to do that very shortly.